Good afternoon, everyone. So in the last class, we have seen how we can write MATLAB programs to perform AM, modulation, and demodulation. Similarly, we have also seen the programs for DSB SC and frequency modulation and demodulation. So in this class, we will see how we can perform the same experiments by using LabVIEW. So LabVIEW is basically a graphical interface. So here in MATLAB, we need to write a code in order to perform any operation. Whereas in case of LabVIEW, it is basically a graphical programming environment. So as you can see here, so when you open LabVIEW, so this is how it will look like. So here we need to go to File and New VI. So here the programs that we write in LabVIEW will be saved as .vi extension. So MATLAB programs will be saved as .m files, whereas this LabVIEW files will be saved as .vi files, as you can see over here, am.vi, dsp.vi. So vi means basically virtual instrument. So we can go to new vi. So now we have two windows over here. So this is the block diagram and this is front panel. So we can press Ctrl T over here so that they will be assigned as like this. So here this front panel means here this is visible to the user. Means, if there are any controls, we can control the circuit by using this front panel, and the outputs and inputs can be given through this front panel. And this is block diagram. That means the internal structure of the circuit. So we need to build the circuit over here, and all the inputs and outputs will be visible on the front panel. So now first let us see the amplitude modulation and demodulation by using this LabVIEW. So here in this basically there will be already predefined blocks will be there. We need to use those blocks and then connect them. So here so in order to perform modulation, first we need a signal source. So you can right click on this block diagram window, and here we can see various blocks available over here. So here we need to go to signal processing menu, and here we can see the waveform generation. So right click on the block diagram window, then go to signal processing, and here waveform generation. So first we need a source in order to generate a sine wave. So in waveform generation, here we have simulate signal option. So if we click here and if we select it, so these are the properties that we can change for this signal generator. So we can choose the signal type, either sine, square, triangle, etc. And here we can give the frequency value, amplitude values, and here we can give the this sampling time, etc. So this block is called as simulate signal. So here by using this block, we can generate a any waveform. It can be either sinusoidal, triangular, or anything. So by using the properties, we can change its amplitude, frequency, and all. So we can rename it. So let us rename it as message signal. We need one more signal generator for carrier signal. So we can simply copy this block and let us rename this signal as carrier signal. So again, in order to implement this amplitude modulation, we again use its equation, standard form of AM equation. So it is given by 1 plus Ka times m of t multiplied by C of t. So here we need a multiplier. So again, right click and go to mathematics. So all these adder, subtractor, multiplier, these can be found in this mathematics menu. We need to right click mathematics, and here in numeric options. So here you can see adder, subtractor, multiplier, and so on. So we need a multiplier, and we also need an adder. So the first part is 1 plus Ka times m of t. So m of t is nothing but the message signal. So this is message signal, and it should be multiplied by Ka. So we need multiplier. So the output from this, so here the sine wave is selected. So this is simply connected to this multiplier, and the other input for this multiplier is Ka, that is the factor which decides the modulation index. So here, as we need to vary this value of Ka, so here we can insert a control over here. So for the multiplier, there will be two inputs. One input is given from the message signal, and at the other input, we need to right click and go to create, and we can create a control. So here, by using this option, we can either create a constant or control. So since Ka is variable, so we need to create a control over here. So this will be control. So whenever we have created the control, you can see that in the front panel, there is one option over here. So here, by using this, we can change the values of Ka like this. So this is the reason why we have created a control option over here. So if it is constant, then we cannot change the value. So since we have created a control, we can change this Ka value during the runtime. So this block diagram, this is the internal structure, and this is the part that is visible to the user. So now, at the output of this multiplier, we have Ka times message signal. So now we need to add 1 to this output. So for this multiplier, this output is given as input to the adder, and the other input will be here. It is simply a constant. So we can go to create and constant. So here, and the value of the constant is 1. So since the AM equation is given by 1 plus Ka times m of t. So this part is m of t. This is nothing but Ka, and here we are giving 1. So at the output of the multiplier, we have Ka times m of t, and when we are adding with this with 1, so here we will get 1 plus Ka times m of t. Now we need another multiplier, and this for this multiplier, one input will be the carrier, and the other input will be from this adder. So here it will be 1 plus Ka times m of t, and it is being multiplied by this carrier signal. So now at the output we have 1 plus Ka times m of t multiplied by carrier signal. So here we have AM signal. We are simply using the message signal and carrier signal, and by using the standard form of equation, we are simply generating by using these multipliers and adder circuits. So for this adder, we have given one input as constant 1. So here the output will be 1 plus this function, and this is nothing but Ka times m of t. So here it will be 1 plus Ka times m of t, and it is being multiplied by carrier signal. So here finally we can easily generate the AM signal. So now in order to observe this waveform, here we need to create a graph indicator. So since we need to observe the waveform, so we need to right click on this output and create graph indicator. So here you can observe, as I have created a graph indicator on the front panel, you can see this waveform graph. So now the output can be observed in this graph. So till now we have created the modulated signal. So first we will see how this modulated signal will look like, and then we need to demodulate the signal again. So now in order to simulate this, we need to give the values of this message signal and carrier signal. So by simply double clicking on this, we get these properties, or we can also right click on this and click on properties. So here the waveform will use sine wave, and the frequency, let this frequency be 10, and the amplitude is 1. And let us take this samples as 10,000 so that the waveform is clearly visible to us. So if we take more number of samples, then we can see the waveform clearly. Similarly, we can change the properties of the carrier signal. So since the carrier frequency should be higher than the message signal, so I'll take this carrier frequency as 100, and again I am here taking the number of samples as 10,000. So now we have given the amplitudes of message signal and carrier signal, and here the value of Ka is given as 0.5. So now if we want to observe the carrier signal and message signal, so here we can again create a graph indicator. So right click on this and create graph indicator. So this will be the message signal. In order to observe the carrier signal, again you can create a graph indicator over here. So rename it as carrier. And then this one is nothing but the modulated waveform, AM signal. So here we can see the message signal, here carrier, and then here we can observe the AM signal. So now in order to run this, here there is a run button over here. So by simply clicking on the run button, so here we can observe the waveforms. This is the message signal, this is carrier signal, and here we can see the amplitude modulated signal. So in order to see the waveform clearly, so here we can change this time index over here. So let us take it as 0.6. Here we can observe this is the message signal and this is the AM signal. So here we can observe that the AM signal is being varied in accordance with the message signal. So this is the case when Ka value is less than 1. So now we can change this value directly from here. Let us take it as 1. Now if we again run this program, so here you can observe that now this is the case when K is equal to 1. Here you can observe K is equal to 1. And for the third case, we can take value of K is greater than 1. So I'm taking it as 3. And if we run the program again, so now here we can observe the over modulation case. Here we can observe there is a phase shift phase error over here. So still we can zoom it over. Here we can observe whenever there is a zero crossing, there is a phase shift of 180 degrees. So I hope it is visible now. So here there is a phase shift of 180 degrees because we have taken the value of Ka as 3, which is greater than 1. So this is the modulation process. So now in order to demodulate the signal, So we can simply use the coherent detection. So in coherent detection, we know that we will use a carrier signal that is generated locally. So we'll use a local oscillator at the receiver side and we will generate the signal. And then if you multiply the carrier signal with the modulated signal and then pass it through a low pass filter, then we can demodulate the signal. So for that, we need a carrier. So I'm simply copying this carrier signal. And we need a multiplier. So for this, the two inputs will be, this is the locally generated carrier and this is the AM signal, modulated signal. So we need to multiply the modulated signal and locally generated carrier. And then we need to pass it through a filter, low pass filter. For that, we need a filter. So again, we need to right click and here in the menu, go to the express option and we have signal analysis. In signal analysis, we have a filter option over here. So right click, go to express, signal analysis and filter. So we need to apply this input to the filter. So here we are giving the input, that is the product of modulated signal and locally generated carrier and the filter signal. So here again we can observe the output by creating a graph indicator. Go to create and graph indicator. So here we can observe the filtered signal or demodulated signal. And we can also observe the frequency spectrum of this AM signal. So for that, again, we need to go to express signal analysis, and here we can observe the spectral measurements block. So by using this block, we can compute the Fourier transform, and then we can observe the spectrum of the AM signal. So we can simply connect this modulated signal, and again by using a graph indicator, we can observe the frequency spectrum. So now, in order to demodulate this signal, so here we need to use low pass filter. So for that, we need to, so here there is filter type over here. So since we need a low pass filter here, so we need to select low pass, and here the cutoff frequency should be exactly equal to the FM, which is frequency of the message signal. So since we have given the message signal frequency as 10 Hertz, so here the cutoff frequency should be 10. And click on OK. Now if we run this program again, so here you can observe this is the demodulated signal and this is the spectrum of AM signal. So this is AM signal in time domain and this is in frequency domain. So here we cannot observe the peaks over here since the scale is around 5 kilohertz. So in order to zoom it, so we know that since the message signal is 10 Hertz and carrier frequency is 100 Hertz, so we'll have the frequency bands at 100, 110 and 90 Hertz. So in order to observe those waveforms, here we can simply reduce the scale to 200. Since I have reduced the scale to 200, so here we can observe there are 3 peaks. So we can see one peak at 100 Hertz. So this is the carrier frequency, and at 110 Hertz, this is the upper sideband, and at 90 Hertz, this is the lower sideband. So now let us try changing these message signal frequencies. So let me change this frequency to 50 Hertz. And then click on OK. Now we will change the carrier frequency to 200 Hertz. Now let me simulate this again. So if I simulate it again, so now if you observe this spectrum, so here now we can observe that. So we have the center frequency as 200 because we have changed the carrier frequency to 200, and then upper sideband at 250 hertz and lower sideband at 150 hertz. So as we have changed the message signal frequency to 50 hertz, so it will be FC plus FM, that is 200 plus 50. So we have three peaks at FC, FC plus FM, and FC minus FM. So like this, we can observe the spectrum. And now if we see the in order to see the demodulated signal, here also we need to change the carrier frequency to 200 hertz because the locally generated carrier frequency should be exactly equal to the transmitted carrier. That is the reason why it is named as synchronous detector or coherent detector. So this is how we can generate the AM signal and then demodulate it. So by simply using the modulation equation, we have generated the AM signal, and by using this spectral measurements block, we can observe the frequency spectrum. And for demodulation, we have used coherent detection. That means the modulated signal is being multiplied by locally generated carrier, and by using a low pass filter, we have generated the demodulated signal. So here now we can observe that the demodulated signal is not equal to the modulated signal. The reason is we have not changed the cutoff frequency over here. So we need to change the cutoff frequency to 50 hertz as we have changed the FM value. Now if we run, so we can observe the message signal. So like this, we can simply generate the AM signal. So this is one program, and the second one is DSB SC, double sideband suppressed carrier waveform. So it is much easier to generate when compared to the AM signal because DSB SC is simply the product of message signal and carrier signal. So for that, so there is no need of this value Ka, so we can delete this. So simply we can give the message signal and carrier signal to a multiplier. So DSB SC will be the product of message signal and carrier signal. So remaining all blocks remain same. So here we can observe the message signal. This will be the carrier, and here we can observe the Fourier spectrum of DSB SC signal. And again, in order to demodulate, we can simply use the coherent detector. So again, let us change these values to 10 and 100. So the locally generated carrier should be exactly equal to the transmitted carrier. And this low pass filter should have a cutoff frequency which is equal to FM. Now, if you run this, so this is the DSB SC waveform. So in DSB SC, we know that there will be envelope distortion, so there will be phase 180 degrees phase shift. And here this is the demodulated signal, which is exactly equal to the message signal. And here, in order to see the spectrum clearly, so we can change this axis scale to 200. So now we can observe that there are only two peaks in DSB SC waveform. So the two peaks are at 110 hertz and 90 hertz. So in DSB SC, as we are suppressing the carrier, so there will not be any peak at the carrier frequency. So we will have only the upper sideband and lower sideband at values FC plus FM and FC minus FM. So we have at 110 hertz and 90 hertz. So similarly, we can also see the spectrum of this message signal and carrier signal also by using this FFT block. So this is how we can generate any waveform by using this LabVIEW.